Okay, so today we are looking at Gibbs free energy. This is our last thermodynamic term. It's seen as delta G. Delta G is a change in Gibbs free energy. And in a nutshell, what it basically is, it's a combination of delta H and delta S, where it's taking the useful energy from a reaction like heat and subtracting from it the either useful or unuseful entropy, depending upon which direction the entropy is moving, combines them to look at what we call the spontaneity of the reaction. If delta G, spontaneity, if delta G is negative, the reaction is going to be spontaneous. Now the AP has taken a turn this year. They always used spontaneous before, and I'm not saying spontaneous is a wrong thing to say, but I need you to understand what it means to be spontaneous. When we say spontaneous, I think a lot of people have the misunderstanding that that means it happens fast. You kind of get that feeling? Okay? And that's not what spontaneity is about. Spontaneity has nothing to do with rate. It has nothing to do with intensity. When you say, oh, it's a spontaneous reaction, people think it's like going to explode or something weird. So what they've done on the AP is kind of replace the word spontaneous with the terms thermodynamically favored. Now, I'm coming off of 17 years of teaching spontaneous. So I'm going to say spontaneous a lot, more out of habit than anything else. I need you to recognize that thermodynamically favored means the same thing. So if they ask you a question, is this reaction thermodynamically favorable, you need to know that that means they're asking, is it spontaneous? So they're probably asking what the sign on that delta G is. Okay? Now there's a couple of equations that we're going to use. The first one that we're going to use is going to be the good old Big Mama. The thing about Big Mama is only good in the world of delta G at 25 degrees Celsius. Only. Delta G is super temperature dependent, and it changes too much with temperature for us to use that table in the back of the book with the delta G's on it for anything but 25 degrees. So given that option, you can use Big Mama. However, if we're not at 25 degrees, we have to use what I call the ghetto-homie equation. I did not make this up. Again, it's another student invention, and it is ghetto-homies take speed. Okay? And if you look up, there's my ghetto-homie, my little cartoon character. At the time, the student I had called me Deems. This was, while everyone else called me Demo, she called me Deems, so that's what's on his little sweatshirt. And then his bubble above, he says, I'm bad, and he thinks he's cool. So that is the ghetto-homie. Not too long ago, the professor from A&M, I got really nervous when I saw the name on the email, emailed me and was like, hi, my name is Professor blah, blah, blah. I teach many of your former students. I do have a question for you. What is with the, or who is ghetto-homie? It was really kind of funny. So, yeah, it works. So just remember, ghetto-homies take speed, and if you're not at 25 degrees, you have to calculate delta H and delta S using Big Mama. Because those, even though they might be a smidge, eensy bit temperature dependent, they're not going to be as seriously temperature dependent as your delta G is. Plug those in, plug in the Kelvin temperature in question, and solve. We use Kelvin because, remember, the units on our delta S are joules per mole K. So that's going to help us with problems like that. Now, a big thing that goes on is determining at what temperatures things become thermodynamically favorable. And it all depends on whether or not the reaction is endothermic or exo or increase in entropy. It's a combination of things. This is a table that, some teachers have their students memorize. I think it's a waste of time to memorize it. We're going to recreate something a little bit different, and it's going to help you understand how to do problems like this. So go ahead and split your page into 4. Okay, and we're going to basically, within this little thing here, figure out at what temperatures are we going to be thermodynamically favorable or spontaneous? And by what temperatures, I mean what range? High temperatures, low temperatures, no, never spontaneous or always spontaneous. We're going to figure that out with different combinations of exothermic, endothermic, and all that kind of stuff. So what do we have to be thermodynamically favorable? What does delta G have to be? Negative. So keep in mind we're looking for a delta G of negative in all of these scenarios. All right, So what I want you to do in each quadrant, go ahead and write ghetto homies 4 times. Not 4 times in each quadrant, once in each quadrant. And this is going to help you practice memorizing ghetto homies take speed. Delta G is equal to delta H minus T delta S. Delta G is equal to delta H minus T delta S. Okay, and so what we're going to do, we're going to examine the combinations, all the possible combinations of H and S, and figure out what range of temperatures will make the reaction thermodynamically favorable or spontaneous. So looking at this, I'll let you guys pick. Do you want an endothermic or an exothermic reaction? Exo. All right, do we want entropy to be decreasing or increasing? I don't hear anything, so I'll say increasing. All right, so what we're going to do is predict at what temperatures will delta G, at what temperature range will the delta G be negative? Because that's what we're looking for, at what temperatures. You have to keep in mind that Kelvin temperatures are never actually negative. So if I have a negative here and I'm subtracting this term, which is always positive, right? When will delta G be negative? Always. So this is going to be a combination where we get always spontaneous or always thermodynamically favored. When we have an exothermic reaction and an increase in entropy. That's always spontaneous. Does everyone see that? Okay, now let's take a look at this next one here. Let's stay with the exothermic, and this time we have a decrease in entropy. What happens to 2 negatives here? It becomes a positive delta, right? So at what temperatures, remember, if we want delta G to be negative, that's going to be our source of negative. So at what temperatures, high or low, or always or never, will it be possible where it's not going to overtake that negative term? Low. So this is only spontaneous or thermodynamically favorable at low temperatures. It's got to be low enough temperatures where that term doesn't overtake this negative term. Because again, we're looking for a negative delta G. So this is an exothermic reaction with a decrease in entropy. Okay, let's try a different one. So now obviously we need to go endothermic. Let's do positive delta H with a decrease in entropy. That becomes a plus plus. Yep, this is never spontaneous or never thermodynamically favorable. And so this is endo and a decrease. So that's a bad combination for a reaction. So do you see how saying something's exothermic doesn't translate to being spontaneous necessarily? It has to be the combination of the entropy of the universe or the system as well as the heat involved. And so here we need to have a positive with a increase in entropy. So here we have an endothermic with a decrease in entropy. No, increase, sorry. Increase in entropy. All right, what about there? Yeah, we want this negative term to overtake that to make this negative, so this is at high temperatures. So you don't need to sit here and memorize a table. All you need to do is look at the reaction. You can either by inspection know, oh, I'm making more moles of gas, and I know that's exothermic, so you can figure it out with things like that. And you can play with the numbers. Okay, so moving onward. Number 5 says calculate delta G for the reaction using, this came from exercise number 1. You all have to flip back and help us find numbers, where we're going to do it 2 different ways. We're going to use Big Mama because they're saying, we're just going to say at 25 degrees Celsius. And then we're going to do it again using ghetto homies. Now, to do Big Mama, number 1 has a table above it that has the value, your delta G values. So delta G, we do products minus reactants. One time, go back to number 1 and tell me what the delta G value for AlCl3 is. Negative 704, and the units on that are? It's not on top of the table? Kilojoules per mole. All right, and then what can you tell me about all the free elements? Products minus, they're all 0. All right, so my delta G here is negative 704 kilojoules per mole. Okay, now I want to do it again, but this time I want to use ghetto homies. You guys have already calculated delta H and delta S for the reaction throughout the in-class problems, so I want you to find those. Holler them out when you get to them. Problem number 1, you found out delta H. No, it can't be. Wait, did you give me delta H instead of delta G? Okay, sorry people at home, he gave me the wrong value. That's negative 629. So this one came out to be negative 704 in problem number 1. And our delta S you guys found in a later problem. Look for it, guys. Come on. No, not of the universe. Of this reaction, you just found the delta S. Negative 199? Negative 199. That's joules per mole. So now we're going to plug those two values, which we use we use Big Mama for, to find the delta G from ghetto homies. Delta H is negative 704 kilojoules per mole minus the temperature we're assuming is 298 here. And then delta S, we got to convert to be the same, so let's just convert it to kilojoules, 0.199 kilojoules per mole. So what do we get? Do the math. Is it not? Nah, that can't be right. When it's done correctly, it's dead on with that previous one. Okay, first off, did y'all give me the correct answers to these? First period had no problem with this at all. Go back to number 1. Is negative 704 correct, or is it positive 704? Okay, go to the other one and find delta S and tell me what its value is and verify that. All right, so let's try it again. Okay, so for those of you at home, I apologize. First period could do it. I don't know what's going on, and I don't have the numbers in front of me. So the answer should be the same. I don't have time to sit here and go over it for a 5th time. So there's something wrong in this that you guys aren't picking up on. And I have a feeling it's the delta S. I don't know why we're having issues with giving me the right delta S. I need you right now to go back to the table, and I'm getting a little irritated. Go back to the table on problem number 1 and recalculate the delta S for this reaction using Big Mama. So due to second period's inability to give me correct numbers, we had a wrong answer, and it's negative 251 kilojoules per mole. There are 28 calculators in here, and from now on, I'm not going to write anything on this board until I get 3 verifications. There's no excuse for us having wrong answers in the in-class problems, and which translates to my videos because you guys can't help each other and check answers. So let's do it again. And the answer is negative 629. So now I have a wrong answer in the videos from the previous day. So those of you who watch my videos, go back to the entropy day and make sure you get a better answer for what number is this in the in-class problems. All right, let's move on. Okay, calculate the temperature at which the reaction occurs spontaneously, or thermodynamic. When does thermodynamic favorability start? Any ideas of what we're going to do with this? What are we going to plug in to get a homies? Okay. Doesn't help me. Not a good enough explanation. Plug in everything but temperature. Okay. I can put in a T for temperature. What do I do for all three things? Calculate delta H and delta G, delta H and delta S. How? Big mama. Then what? I can't calculate delta G because I don't know if I'm at 25 degrees Celsius. So what do I do? What would that be? The point at where it would be positive or negative. What would be a good thing to plug into delta G? What? 0. I'm going to plug in 0 for delta G because that's the cusp. That's the point at which either if I increase or decrease temperature, depending upon what direction the reaction is, like depending upon the signs, that spontaneity is going to occur. So we're going to plug that in. Good Lord, and I hate to even do this now because it's going to be the same issue as before. First 3 rows. I need you guys using the data on the board. I took all the numbers off of the data table. I need you guys to utilize this information to calculate delta H using Big Mama. I want 3 verifications on answers. The next 3 rows, you guys will calculate delta S. And I want everybody to convert to joules. So currently they are using Big Mama to solve for delta H and delta S. The values have been taken from a thermo table. I'm under the assumption that they know how to do Big Mama because we did it in thermochemistry. All right, holler out a delta H when you get one. We'll verify it. And I want it in joules. $176,000 joules per negative 176,000 joules per mole. That sounds familiar to me from last period. All right. So minus. Now, we're looking for the temperature at which this is going to start to become spontaneous. And so my delta S, you'll already have it in joules. What did you guys get? All right. So we have a correct answer for that. All right. So now go ahead and solve for your Kelvin temperature. What? This is negative? Guys, you can't read me numbers and not put negatives in front of them because that is just as important as the actual number. 618 Kelvin. So that's the point at which thermodynamic favorability occurs. But is it really spontaneous above or below that? Look at your signs. This is really a positive. So correct. So any temp below this will give a delta G that's negative. All right, you have to realize it's not just one temperature that something's going to be thermodynamically favorable at. It's going to be a range of temperatures. All right, let's go on. So what we're going to do is, rather than, if you notice this question says, how does delta G change when the temperature is increased? They're not asking you for that exact value. When they don't ask you for the exact T, you can just look at ghetto homies and look at the signs based on the information you already know. We're revisiting that number 1 problem again. So if I want to know how the temperature changes as I increase, how the delta G changes as I increase temperature, I need to look at the signs of all this. What was the delta H of this reaction from problem number 1? The sign. Negative. It was negative 7 something. What about the delta S? I don't care about exact numbers, again, because I'm just looking at as temperature changes, what happens. That's negative as well? And let's verify that. We're going from solid to liquid to all solid. So yeah, that makes sense that that delta S is negative. All right, so since that's negative, this becomes positive, positive. So as I increase the temperature, what's going to happen to my favorability? It decreases, right? So this is going to become less thermodynamically favorable as temperature increases. Temperature increases. In other words, it's going to go from possibly spontaneous to not spontaneous as we increase temperature. Got it? Okay, with this one, just to save me some work, because I don't like to do work, I can figure out the sign of delta S just by looking at the equation, can I? What's going to be the sign of the delta S? What's happening to disorder? Yeah, it's positive. We're getting from 1 mole of gas to 2 moles of gas, so we know that's going to be positive. I don't know anything about the delta H here, unfortunately. That's just because I don't have any experience with this reaction, so I'm going to have to use Big Mama. You have your delta H's on the board, and it's going to be Big Mama 2 times 33.18 minus 1 times 9.16. Is that going to be a positive or negative number? It's positive, correct? So since that's positive, as I increase the temperature, what happens to this reaction? It's going to become more, and it's hard to say more spontaneous. What does it mean? Either you're spontaneous or not, right? So it's going to become more thermodynamically favorable, meaning it could go from non-spontaneous to spontaneous as temperature increases. Favorability increases. All right, let's do it for the last one. The last one, I'm not going to do any math at all because I know enough about this one just from my experience to come up with the signs of all of these things. The first one is always easy to look at is your entropy. What's going on there? Yeah, it's becoming more moles of gas. So we're going from gas to liquid to all gas. So that's going to be a positive. Now what about this delta H business? What does that reaction look like? You've kind of seen it. You should kind of recognize it. What? It's no. You can't look at signs. You can't look at phases to determine exo or endothermic. But you said something. Is it combustion? It's a reverse of a combustion. All combustion reactions are exo. This is the reverse of a combustion, so it's endo. So this would be positive. Got it? You see how that's the reverse of a combustion? Okay. Looking at this then, as I increase this temperature, what's going to happen? It's going to get more spontaneous, or it could go from non-spontaneous to spontaneous. More thermodynamically favored as temp increases. Got it? Okay. With these, I'm really only going to do one problem on this page, and that's part B. We really don't need to do these. Okay, so we're looking for the temperature at which this reaction becomes spontaneous. What? Put 0 in for delta G. And we're going to solve. Does anybody have anything to say about this before we do it, though? Wouldn't it just be 100 degrees Celsius? What's going on here? This is vaporization, right? Well, we're going to prove it. 100. See how close we're going to get. It reminds me of one thing I need to talk about delta G. Don't let me go on until I'm done talking about phase changes and equilibrium. All right. So 100 degrees C is kind of what we're going to predict. So let's go ahead and solve. First 3 rows, I want you to do delta H. Next 3 rows, I want you to do delta S. I have the water. It's just gas minus liquid, products minus reactants. And let's all go to joules. Let's get in the habit of going to joules. Delta H, someone throw it out and we'll verify it. Gas minus liquid. Negative 44,000. All right, and then delta S. Isn't it 44,000 and like 12 or something? Yeah, no need to round here. And then delta S. And this is joules per mole. This is joules per mole K. Go ahead and solve for temperature. (370). If we're converting to degrees Celsius and then rounding to 1 sig fig, we get minus 273. What is that? And let's round it to 1 sig fig. 100 degrees Celsius. Okay, so we just derived the boiling point of water using this equation, using thermodynamics, which is pretty cool to be able to do that. Okay, we basically have done this next problem. We're not going to do it again, obviously, but what's important that you need to know about delta G? What does it mean to be at equilibrium again? The rate of the forward and the rate of the reverse are the same, which really means that there is a forward reaction and there is a reverse reaction going on simultaneously. So if I have a forward going on, it means it's spontaneous in the forward direction. But if I have a reverse going on, doesn't it mean it's spontaneous in the reverse direction? So if I've got both of those equal and opposite, what do you think delta G is at equilibrium? 0. At equilibrium, delta G is 0. And that's why we were allowed to plug in to that H2O thing, and it didn't have equilibrium arrows. It really should have. H2O liquid to gas, because this is the phase change, and that's another thing that's important. It's really important that you realize that every phase change at a temperature at which you have that going on, what is delta G? At phase changes, 0. So at equilibrium, or at phase changes, which is a relationship at equilibrium, our delta G is always 0. You need this in your bag of tricks because they're going to try to talk to you and say, oh, ethanol vaporizes at this temperature. Calculate delta G. And you'll be like, or they'll say, what is delta G? And they won't give you a thermotable. And you're going to be like, well, I don't have a thermotable. I can't do ghetto homies. How do I know what delta G is? Because it says it's vaporizing at a certain temperature, they're telling you that's at its phase change. That's at equilibrium. Therefore, delta G is 0. So you really need to know that piece of information. Okay? All right, so this is where I'll start on the video for tomorrow in case we are not here and we're iced out. All right, that's it.